Hi, and welcome to our talk on the empirical evaluation of pre-training strategies for supervised entity linking. I am Thibault, and this is work with my colleagues Nicholas, Livio, and Tom from Google Research. Our contribution is a four-layer transformer and entity embeddings that achieve state-of-the-art performance on the CoNLL and TAC-KBP entity disambiguation tasks. The same model also achieves strong results on end-to-end entity linking and entity linking without in-domain data. Through careful ablation studies, we show the importance of negative candidate selection, of input perturbation, and of context selection. Entity disambiguation maps the specific textual mention to its corresponding entity in a target knowledge base. In this case, we have to distinguish the great basketball player Michael Jordan from the even greater researcher. Traditionally, entity linking approaches have relied on knowledge bases, complicated modeling, and task-specific and engineered features. More recently, approaches have shown that using BERT and pre-training on Wikipedia entity links is effective. However, these approaches have focused on constructing general-purpose entity representations, building strong zero-shot entity linking systems, and end-to-end entity linking, so that the limits of pre-training for entity disambiguation have not yet been fully explored. We use Wikipedia as our training data, using its hyperlinks as supervision signal. We derive 17 million links for 5.7 million unique entities. Our model is a four-layer transformer where each pen is represented by the concatenation of its start and end word piece, and we project this through a multi-layer perceptron. For entity disambiguation, those spans are provided by the data, while we predict them for our end-to-end entity linking results. Finally, we score each potential entity by taking the dot product with the entity embedding. We train our model with cross-entropy loss normalized over a set of candidates. Computing scores over the 6 million entities is expensive. Therefore, we explore methods to define a tractable set of hard negatives, which we describe next. Page candidates are negatives that are the other entities mentioned on the same page. These tend to be semantically, but not lexically related to the target mention. Phrase table candidates are the other entries in an alias table for a mention. Finally, random entities are added for robustness. In addition, we also explore adding the same input perturbation as BERT. This enables our model to learn that either Michael or Jordan might refer to Michael Jordan. We found that while this input perturbation was helpful, we did not get additional performance benefits from using an auxiliary math language modeling objective. We evaluate our model on two of the most popular supervised entity disambiguation datasets, CoNLL and TAC-KBP. CoNLL is 1,400 densely labeled newswire documents. Its entity set is the whole Wikipedia. We use two different alias tables for this task, the one originally provided with the dataset and the high-precision one used by most state-of-the-art systems. In contrast, TAC-KBP is sparsely labeled and is limited to 850,000 entities. Since the candidate set is much smaller, we do not use an alias table at inference. Moving on to our results. On CoNLL, our model significantly improves on the existing methods. On the high-precision alias table setting, we achieve an error reduction rate of 36%. On TAC-KBP, our four-layer model compares favorably against the 12-layer transformer initialized from BERT. With simple modeling changes, including the addition of a mention prediction layer, we can achieve strong results on entity linking without any task-specific modeling. Now to our ablations. We find that candidate selection matters, especially without in-domain training data. On CoNLL, using alias table candidates is key, since that is similar to the setup used at evaluation. On TAC-KBP, where we do not use an alias table at evaluation, random candidates are particularly helpful. Closely matching the pre-training setup and evaluation setup is important on this task. Similarly, input noising is helpful, especially without in-domain training data, adding 4 points on CoNLL performance. Finally, we conduct qualitative error analysis, which shows that we are close to the accuracy upper bound on this task. For instance, we believe that our model's prediction is actually valid here. Thanks for listening to our talk.